Hello and welcome, and in this video we're going to be talking about operations with complex numbers. So we're going to be talking about adding, subtracting, multiplying, and dividing complex numbers, okay? Now, before we talk about adding and subtracting and all that stuff with complex numbers, I want to introduce it with just a standard polynomial type problem. So adding two binomials, for example. Well, this is straight from Algebra 1, right? And when we're adding binomials, all we're really doing is we're combining like terms, right? So I would combine the 2 and the -3 and make that -1. And I would combine the 3x and a -4x to become -x, and that would give me my final answer of -1 minus x, right? Well, adding complex numbers is actually pretty much the exact same. So if I had two complex numbers, which remember the standard form of a complex number is a plus bi. So if I had 2 plus 3i as one complex number, adding the other complex number of -3 minus 4i, well, I would once again combine like terms. I would combine the real parts, and the real parts are 2 and -3. When I combine those two, I'm ending up with -1. And I'm going to be combining the imaginary parts of 3i and -4i. So I'm going to be combining the imaginary parts of 3i and -4i to get -1i, which leaves us with our final answer, -1 minus I. And that's it. That's all that adding complex numbers is. But make sure it is in standard form. The real part is always going to come first, and the imaginary part is always going to come second. You always need to make sure that your final answer is in standard form, all right? So if we had a completely new problem, say for example 14 minus 9i plus -3 plus 11i, I would do the exact same system. I would combine the real parts. So I would combine the real parts of 14 and -3, and that would end up getting me 11. And then I would combine the imaginary parts of -9i and positive 11i to get positive 2i, and I would make sure my answer is in standard form, 11 plus 2i, and that is it. That would end up being our final answer, 11 plus 2i. So adding complex numbers is really no different than just adding polynomials in general, and you'll find the exact same when we talk about subtracting complex numbers. All right, so let's take a look at a subtraction problem. Now, once again, I want to introduce it with subtracting polynomials, okay? We got two binomials subtracting right here. Now, what you would normally do, right, is you would distribute the negative to everything in the second polynomial, and then you would combine like terms. So I distribute the negative to the 2 and a -5x, so that's -2 and positive 5x now. And now you would combine like terms. You would combine the 7 and a -2 to get 5, and you would combine the 3x and the 5x to get 8x. Now, the way that we subtract complex numbers is basically the exact same idea. So instead of having 3x and -5x, I just change it to 3i and -5i. We would once again distribute the negative to the 2 and a -5i to get -2 plus 5i, and now we would end up combining like terms. So I would combine the 7 and a -2, which are the real parts, to get 5, and then we would combine the imaginary parts, 3i and 5i, to get positive 8i. And once again, make sure your answer is written in standard form, real part first, imaginary part second, so our final answer would be 5 plus 8i. So that's how we subtract complex numbers. So let's take a look at just one extra example there. Let's say we had something like this, 4 plus 5i minus -2 plus 9i. Well, once again, we would distribute the negative to everything in the second complex number to get 2 minus 9i. And now we would combine the real parts, 4 and 2, to get positive 6. We'd combine the imaginary parts, 5i and -9i, to get -4i, and make sure it's in standard form, which it already is. So 6 minus 4i would end up being our final answer. So that is subtracting complex numbers. So in the next example, I want to talk about multiplying complex numbers. All right, so now let's talk about multiplying complex numbers. Now, once again, I'm going to introduce it by multiplying two binomials together. Now, if we were multiplying these binomials together, right, you would distribute the 2 to everything in the second binomial. So we'd get 8 minus 2x because we distribute the 2. Then once we distribute the 2, we would now distribute the 3x everything in the second binomial to get 12x minus 3x squared, right? And then we would combine like terms. We would combine a -2x and a positive 12x, and then write it in standard form, which would be -3x squared plus 10x plus 8. Now, multiplying complex numbers is very similar. So if I was multiplying 2 plus 3i and 4 minus I would do pretty much the exact same thing. I would first distribute the 2 to everything in the second complex number, and that would get me 8 minus 2i. From there, I would distribute the 3i to everything in a second complex number to get 12i and negative 3i squared, right? Once again, combine like terms to get 8 plus 10i minus 3i squared. However, in the standard form of a complex number, there is no I squared. The standard form of a complex number is a plus bi, so what in the world do we do with that I squared? Well, remember, this is actually where the powers of I come into play, because I squared, remember, is equal to the very real number, -1. So what we need to do is then substitute in -1 anywhere that we see an I squared, and then we will be able to have it in the standard form. So whenever you see an I squared or I cubed or I to the 4th or something along those lines, you are going to need to use substitution. The standard form of a complex number does not have I squared or I cubed or anything like that. It is simply a plus bi. So we substitute in -1 for I squared to get 8 plus 10i, and that's now plus 3. And then finally, we have some like terms we can combine. We have 8 and 3 we can combine to get 11 plus 10i. Okay, so let's go ahead and take a look at another multiplication problem. All right, so let's take a look at another multiplication problem. So we have -4 minus 3i times 2 minus 2i. Now, just like with any other multiplication problem, as if we were multiplying two binomials together, we would go ahead and distribute the first term into everything in the second polynomial, where in this case, we're distributing the -4 to everything in the second complex number. So we get -8 plus 8i. Then we are going to go ahead and distribute the -3i to everything in the second complex number to get -6 plus 6i. From there, we are going to have some like terms. We have 8i and -6i, so we can combine those to get -8 plus 2i plus 6i squared. Now from here, we need to remember that I squared is equal to -1. So wherever we see an I squared, we are going to substitute in a -1. So this is now -8 plus 2i plus 6 times -1, because that was 6i squared. And then from there, we are going to get -8 plus 2i minus 6. And as you see, we now have some like terms of -8 and -6 to get -14 plus 2i. And that would be our final answer. It does not matter that the first term is negative. The standard form of a complex number is always real part first, imaginary part second. So -14 has to come first and positive 2i has to come second. So that is multiplying complex numbers. Now let's take a look at dividing complex numbers. All right, so we're just going to jump right into dividing complex numbers because it's actually a little bit different to divide polynomials as it is to divide complex numbers. And dividing complex numbers actually turns into a big multiplication problem. Now, the reason why we can't have this is because you need to remember that I is a square root. I is a square root of -1. So what this is basically saying is we have 2 minus the square root of -1 in our denominator. And remember, we cannot have radicals in our denominator, so that means we cannot have I in our denominator. So the way we combat this is we use something called the complex conjugate. So the complex conjugate of 2 minus I is actually going to end up being 2 plus I, because all we do is we switch the sign of the imaginary part. And the reason why complex conjugates are important is because when you multiply two complex conjugates together, the imaginary parts cancel out. So when we multiply 2 minus I by its conjugate, the i's are going to cancel out, which means we no longer have a square root in the denominator, and that's what we need. So like I said, the conjugate of 2 minus I is 2 plus I, because all we do is we switch the imaginary part sign. We do not switch the real part sign. So 2 minus i's conjugate is 2 plus I. Just like if I said -4 minus 5i, its conjugate would be -4 plus 5i. We only change the sign of the imaginary part. So now this becomes a big multiplication problem. So we're multiplying the numerator and the denominator by 2 plus I, because what we do to the numerator, we have to do to our denominator. That way we don't actually change the problem. Because if I look back right here, all I'm doing is multiplying by 1. Anything divided by itself is 1. So what I'm really only doing is multiplying by 1, but I'm doing it to get rid of the I in the denominator. So we multiply the numerator and denominator by the conjugate of the denominator. And now we start multiplying. So we distribute the -10 to 2 plus I, and we get -20 minus 10i. Then we distribute the negative 7i to 2 plus I to get negative 14i minus 7i squared. And we're going to do the exact same thing with our denominator. Distribute the 2 and distribute the negative I. And now we can start combining like terms. So I can combine negative 10i and negative 14i. And we also need to remember that I squared is equal to negative 1. Once again, we cannot end up having an I squared in our answer. And from there, we're going to simplify the denominator. Once again, we distribute everything, so we combine like terms, and that's where the i's cancel. We notice a 2i and a negative 2i, they end up canceling each other out, and that's what we need to happen. So this is simply going to become 4 minus I squared, but remember I squared is negative 1, so this becomes 4 minus negative 1. And from here, it's just combining like terms and making sure it's written in standard form. So we combine like terms to get negative 20 minus 24i plus 7, and then 4 plus 1, and then we combine like terms, to get negative 14 minus 24i all over 5. Now, I'm okay with this being written as an answer. Just know, in a lot of cases, you're going to want to split that up into two fractions, especially because you might be able to simplify one of those fractions. So we would actually write it as negative 14 over 5 minus 24i over 5. So the real part of this complex number is negative 14 fifths, and the imaginary part is negative 24i fifths. And that would end up being our final answer. Okay, so that would be our final answer. Let's cover just one more division problem because these can be a little tricky. All right, so let's take a look at this other division problem. Now, remember, once again, we cannot have I in our denominator because that is the same as having a radical in our denominator. So what we're going to have to do is multiply by the conjugate of the denominator. And the conjugate of negative 9 plus 8i would be negative 9 minus 8i. So we're going to multiply both the numerator and denominator by negative 9 minus 8i. And like I said, remember, division problems actually turn into multiplication problems with complex numbers. So we're going to go ahead and multiply out that numerator to get 153 plus 136i plus 9i plus 8i squared. And we're also going to multiply out the denominator to get 81 plus 72i minus 72i minus 64i squared. And now we're going to go ahead and combine like terms and substitute in negative 1 for I squared. So that's going to end up looking like this. This is our numerator. We can combine 136i and 9i to become 145i. And like I said, we substitute in negative 1 for I squared. We do the exact same thing with our denominator. And remember, that's why we multiply by the conjugate of the denominator, because the 72 i's cancel out, which means that we no longer have an imaginary part in our denominator, which means we no longer have a radical in our denominator, which is what we need to happen. So from there, we go ahead and we keep simplifying. So I'm going to multiply each of those terms by negative 1, as you see here. So this will become 153 plus 145i minus 8 over 81 now plus 64. So that's going to end up becoming 145 plus 145i all over 145. And remember, you're going to want to split that up and simplify if you can. And this one simplifies ever so nicely. This simplifies to 1 plus I. And that would end up being our final answer. And that is operations with complex numbers. I hope this video was helpful. If there's any questions, please feel free to let me know. And I look forward to seeing you guys in upcoming videos.